Now this is what a typical FTIR spectrometer looks like. We still kind of have the same basic idea, but instead of a monochromator, now we have this interferometer to be able to distinguish not distinguish, but measure all of our different frequencies. So we have our light source down here, and we actually, in most FTIRs nowadays, there's also a laser, or I should say all. And the laser is a necessary part of this because it allows us to measure the exact distance traveled, and also is a way to digitize. It gives the instrument a way to measure, like, how often do I need to measure the signal on the detector. And so we know the wavelength of this laser really well, which lets us calibrate all the interferograms that we have. So the laser is basically just here for the interferometer. And so our light source, the light gets sent into the interferometer. We have our stationary mirror on this side and our moving mirror on this side that's moving back and forth like this. And the light then, after it recombines in the interferometer, goes through our sample, and then we have some sort of infrared detector on this side over here. And so just like with any other spectrophotometer, we would measure a blank, and then we measure our sample. And so to get absorbance, we need both the background as well as the sample signal. So one of the key benchmarks of FTIR is the resolution, our ability to resolve closely spaced peaks, just like with the monochromator. But the way that this is determined is different than in a monochromator because we don't have a grading, and so we can't use that same equation we had before. So the resolution instead is given by this equation, and this is approximate, this is an exact value, but it's 1 over this capital delta. Delta here represents the maximum path difference between our two mirrors. And essentially this is 2 times however far this mirror will travel. And that's because the light travels to the mirror and back, and so it's twice whatever that difference is between them, whatever distance this has traveled. And so just as a final thing, just again to show, when we actually do an absorbance spectrum, we have to measure first a background interferogram, which gives us a background spectrum. So this is the, what you would actually see with a real FTIR. So your interferogram is going to look like some squiggly signal like this that doesn't really look like anything. But once you transform it, you get what's your signal as a function of frequency. And then when you have a sample there, you're going to see some dips. This is from the light being absorbed. And once you take that, this is plotted as a transmitted spectrum, but we can then convert that into an absorbance spectrum if we want. So we can use either one. Some of the key advantages of FTIR and why it has really replaced dispersive instruments throughout the infrared is fast acquisition times, because we can measure the entire spectrum all at once. We don't have to scan a monochromator, and so you can acquire an entire spectrum in less than a second. The signal to noise ratio is better than it is with a monochromator because you use all of the light going onto the detector instead of throwing away most of the light and only getting the colors that you want. The frequency accuracy is very helpful, and that is from the way interferometers work. You inherently get the correct frequencies from it. And because of those things, it's very easy to average a lot of spectrum, which can decrease the noise level in your spectrum and allow you to measure things that otherwise would be fairly noisy. And so because of these key advantages of FTIR, it has really come to replace any other type of infrared spectrometer for broadband infrared spectroscopy. And so in the final part that we'll get to next, we'll talk about noise and why averaging Specter is so useful.